In this video, I'll show you how you can calculate a two-sample t confidence interval for the difference between two averages. In this example, a delivery company is investigating how long it takes drivers to deliver goods from the factory to a port for export. From previous records, 44 randomly selected delivery times along the same route, we're going to call this route A, yield a sample mean of 437.2 minutes and a sample standard deviation of 18.3 minutes. A newly proposed route, we're going to call this route B, has been driven 34 times with a sample mean of 403.5 minutes and a sample standard deviation of 15.6 minutes. We want to calculate the 95% confidence interval to estimate the difference in average route times. So we want to calculate the 95% CI for mu A minus mu B, where x bar of A is equal to 437.2, x bar of B is equal to 403.5, S of A is equal to 18.3 minutes, S of B is equal to 15.6 minutes, and our sample sizes are as such, where NA is equal to 44 and NB is equal to 34. Notice how I'm using the subscripts A and B. This is just so I can keep track of route A and route B. Rather than 1 and 2, I can be more specific. All right, so once we've actually obtained each one of the pieces of information we need to calculate the confidence interval for, we need to make sure that our conditions are met. So we need to have random samples or random trials. In this case, we definitely have random samples from our sample size in the fact that we have it stated up here in the problem. So it says 44 randomly selected delivery times. But then for the route B, it just says that was driven 34 times. So maybe this isn't completely random, but perhaps it's still representative. So we're going to check this off as met. The next thing is that we need to have large enough sample sizes. Well, 44 plus 34 is definitely greater than 30. So we have a large enough sample size condition here to calculate then the two-sample t procedure confidence interval. The formula for this is x bar A minus x bar of B plus or minus a t critical value times the standard error, which in this case is SA squared over NA plus SB squared over NB, which we can simply just plug in the values from over here into this formula. However, we should actually first find out what our t critical value is. So there's actually two ways in which we can calculate our degrees of freedom. So if we need to calculate the degrees of freedom and we're doing a two-sample procedure, then the approximate degrees of freedom are the Satterthwaite degrees of freedom. This will give us a more precise estimate. This is equal to the formula, which is pretty nasty, SA squared over NA plus SB squared over NB, all squared, divided by, so the denominator, scroll down a little bit, is equal to SA squared over NA, all quantity squared, all over NA minus 1 plus SB squared divided by NB, all squared over NB minus 1. So this is kind of a nasty formula. It looks really nasty, but essentially all you need are the sample standard deviations and the sample sizes in order to calculate this. So if we plug in the values from our problem, we'll get a numerator value of 218.12 and a denominator value of 2.9. This will give us a degrees of freedom, or Satterthwaite degrees of freedom, of 75.22. If you're using software or a calculator, this is the degrees of freedom that your calculator or software will use. If we're doing this by hand, we should always round down. So it's a whole number, so we can look that up on a table. This is 75. The second issue is that if this is not actually on our table, then we have to round down again until we find the next degrees of freedom. So let's go ahead and go to our T table to see what our T critical value is using the Satterthwaite approximation. If we use 75 degrees of freedom from our T table, we can see that 75 isn't on our table, so we always have to round down to the more conservative estimate. In this case, that's going to be 60. We scroll across the row until we match it up with the column that we're looking at, and in this case, that's going to be 2.00 for our critical value. So the critical value using the Satterthwaite degrees of freedom will be 2.00. Now, another way that we could calculate the degrees of freedom is the minimum degrees of freedom. So this is the conservative approach, which is the degrees of freedom will be the minimum between the 2 degrees of freedom from the individual samples. So in this case, that would be 43 and 33. Essentially, 44 minus 1 and 34 minus 1 would give us these values. So this would mean that the conservative degrees of freedom would be 33. And if we're looking this up on a table, then this would, of course, be 30. Since we've already calculated the Satterthwaite degrees of freedom and it'll give us a better estimate, we're going to use that critical value in our formula. So let's go ahead and plug in the values for our confidence interval. Now that we have all the things that we need to plug in, we're going to put in our X bar A, which in this example was 437.2. So that's 437.2 minus X bar B. So the average from the second root is 403.5 plus or minus a T critical value of 2.0 times the standard error of 18.3 squared all over the sample size of 44 plus 15.6 squared, all divided by the sample size of 34, and we'll get a point estimate of 33.7 plus or minus again, the critical value of 2.00. With a standard error, this comes out to be 3.84. And if we keep going, we'll get, again, our point estimate of 33.7 plus or minus a margin of error of 7.68, which gives us a 95% confidence interval between 26.02 and 41.38. So what does this mean? If we were to interpret this confidence interval, we could say, on average, the newly proposed root, aka root B, is 26.02 minutes to 41.38 minutes faster than the old root, or essentially root B or root A. This is how you can calculate a 2-sample T confidence interval.